Now we're going to get into the real meat of calculus. There were two problems that mathematicians were trying to figure out before calculus was invented. One was, how do you find the tangent line to a curve? And they needed calculus to figure that out. So here's what they did. They were trying to find the slope of the tangent line to a curve at a point. They were using the limit definition, and they came up with a derivative. And then we're going to try to understand the relationship between differentiability and continuity today. So, calculus grew out of four major problems that European mathematicians were working on during the 17th century. First of all, the tangent line problem. That's the big one, and they could solve that. Once they solved that, they were able to figure out velocity and acceleration problems and minimum maximum problems. And then the other big topic, which we'll deal with later, is the area problem. So the derivative is going to help us with numbers 1 through 3. And then the area problem is, how do you find the area under a curve? We'll deal with that in the second half of this year. Each problem involves the notion of a limit, that idea of a limit that we've been working on this chapter, the first chapter. And calculus can be introduced with any of the four problems. So we're going to introduce calculus with the tangent line problem, and then work from there to velocity and the minimum and maximum issues. So here's the tangent line problem. We've got a curve, and we want to find a tangent line. However, all we know how to do right now is to find the equation of a line between 2 points. So if we had two separate points, we could find the equation of that line. We would just do rise over run to get the slope, and then use point slope form to figure out the equation using one of these 2 points. But we don't have 2 points. If what we're trying to do is find the tangent line to a single point, let's say we want the tangent line to this one point right here. If we're trying to find a tangent line that just touches the curve at that one point but doesn't cross it, then we only have 1 point, and it's impossible to find the slope at 1 point, or at least it was until we had calculus. So mathematicians came up with this big definition, and all it is slope. If f is defined on an open interval containing c, so first of all the function has to be defined, which means there can't be any holes, jumps, oscillations, vertical tangents, in between two variables that contain c. The limit, we're going to call that this delta x, that's the change in the x value. We're going to try to find the limit as delta x approaches 0 of the change in y over the change in x. Now let's go back and check this out. If we have this value here, we'll call it c, and this value is a little bit higher than c. So c plus a little bit, a change in x. Then the difference between them is delta x. And what mathematicians decided to do was say, well, what if I took 2 points and squeezed them really close together so that this value approached 0? So that we took this point and then this point, and they're pretty close together, but what if we made them these 2 points? Now they're closer together. Or these 2 points, now they're closer together. Or these 2 points. And kept decreasing the distance between the 2 points until the distance between C and the point next to it was so minuscule it was almost 0. But technically we would still have 2 points. They're just really close together. Then we could find the slope between them. It would be the y value of the second point minus the y value of the first point. That would be the change in y. So if we blow this up, here's our big triangle here. This distance actually represents a very tiny distance, and this is the y value differences. So we are finding slope of 2 points that are very close to each other, so close to each other that the difference between c and c plus delta x is very small, almost 0. So the change in y is the rise, and the change in x is this delta x, that's the run. So this limit definition basically is finding the slope, and that's the rise, and that's the run. So writing it out f of c plus delta x is the y value of the second point that's very close to the first point, minus the first point, the y value of the first point, divided by the difference between the two x values, which is very small. It's approaching 0. So you see that that is just a slope definition. It's just y2 minus y1 over x2 minus x1, but the difference between these 2 points is so tiny that it's almost 0. So that's the slope of our tangent line at any point C. So what we're doing is thinking about trying to find the slope between 2 points, but the 2 points are so close together that they're almost 1 point. And as that limit approaches 0, when you find that limit as delta x approaches 0, you technically are finding the slope at 1 point. That's what a limit does. It's reducing that distance between them so much that it's almost 0, that you are finding the limit at 1 point. Here's a follow-up. If f is continuous at C, so no jumps, no holes, no asymptotes, no oscillations at C, and your limit, which is your slope, equals infinity, or your slope equals negative infinity, then your tangent line is vertical. So does that make sense? If you're trying to find the tangent line to a graph and you end up with the slope of that tangent line being undefined or infinity, then that must be a vertical tangent line. Okay? So for example, this graph at C, that tangent line is vertical. Now I know we've talked about in the past that tangent lines can't cross a line, but if the graph becomes vertical at that point, then the tangent line actually does cross the curve. So a graph could have a vertical tangent line if the limit as delta x approaches 0 of the difference in the y values divided by the difference in the x values equals infinity or negative infinity. Then you have a vertical tangent line. Let's do an example. Find the slope of the graph f of x equals 2x minus 3 at the point 2, 1, using the limit definition of a tangent line. So our limit definition is the limit as delta x approaches 0 of f of 2, because that's the point we want to find the limit at, we want to find the slope at, f of 2 plus delta x minus f of 2 all over the difference between the x values, which would be delta x. So first we need to find f of 2 plus delta x. And remember to plug in 2 plus delta x in place of the letter x. Don't just add on delta x at the end. So we're going to have 2. Okay, made a mistake here. I'll go back. Oops. Sorry. So f of 2 plus delta x, plugging in 2 plus delta x in for x, we're going to get 2 times 2 plus delta x minus 3. So that simplifies to 4 plus 2 delta x minus 3. So that simplifies to 2 delta x plus 1. And now we need to find f of 2. So plug 2 in for x in the function 2x minus 3, and you get 4 minus 3, which is 1. So now we're going to substitute. Limit delta x approaches 0. F of 2 plus delta x is the 2 delta x plus 1. Do I have that right? 4 minus 3? I think so. And then minus 1 from the f of 2, and then delta x. Continuing to simplify, the 1 minus 1 simplifies to 0, and then we're left with that. Keep simplifying, and the delta x's cancel, so we're left with 2. And the limit of a constant is just the constant. So the slope of the graph of 2x minus 3 at 2, 1 is 2. Well, if you had thought about it, we know that the graph of 2x minus 3, y-intercept of 3, slope of 2, is going to have a slope of 2 everywhere. So of course it would have a slope of 2 at the point 2, 1, which is right there. That tangent line is actually on the line. Just using a basic example to use the limit definition to show you that you do get the slope that you would expect. Now this one, f of x equals x squared minus 3, we could not figure out the slope of the tangent line at x squared minus 3 at 2, 1 without using this limit definition, because we don't know what the slope of this graph is. So let's try this one. We're going to do the limit definition, and you do have to have this definition memorized. So f of x plus delta x at 2. So we're going to plug in a 2 here. So this is a 2, and that's going to be a 2. X squared is going to be replaced with 2 plus delta x squared, and then minus 3. So simplifying that, if you do FOIL, you get 4 plus 4 delta x plus delta x squared, and then minus 3. So simplifying that, you get 1 plus 4 delta x plus delta x squared. And then f of 2 is 2 squared minus 3, which again is 1. So replacing, f of 2 plus delta x is 1 plus 4 delta x plus delta x squared minus f of 2, which is 1, all over delta x. Continue to simplify. The 1's cancel out, so we have 4 delta x plus delta x squared all over delta x. You can factor out a delta x, so we have 4 plus delta x inside the parentheses and delta x in the denominator. Now we can cancel those, so now I'm just going to take the limit as delta x approaches 0 of 4 plus delta x. Direct substitution leads to 4 plus 0, which is 4. So the slope of a tangent line that would go through the point 2, 1 of x squared minus 3 is going to be 4. If we quick look at a graph of that, it's a parabola at 2, 1. We're going to have a positive slope, pretty steep, about, whoops, that's not 2, 1, whatever, here. Pretty steep, about 4. That should make logical sense. That's not a proof, that's just checking to see if our answer is does even make sense. All right, so the definition of derivative. A derivative is a slope. The limit that we use to define the slope of a tangent line is also used to define one of the 2 fundamental operations of calculus, differentiation. Now there's a lot of vocabulary here that's going on. A derivative is a noun, it's a thing. Differentiation is what you do to get that thing. So if you differentiate something, you are finding the derivative. So finding the derivative is just another way of asking you to differentiate. They mean the same thing. Finding the derivative, differentiating, they mean the same thing. The derivative of a function is the limit of f of x plus delta x minus f of x all over delta x. And we can use the x in there because we might want to find a derivative at any certain point x for any x, not just a specific number, like not just at 2. So we're going to leave our x in there, and we'll find the derivative, which is the slope of the tangent line, at any certain point x. The notation for derivative is f prime of x, and that's how you say that. F prime of x is the limit of delta x, limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. All right, so we're going to find a derivative which is really just finding the slope of the tangent line using this limit definition. Okay, I think I just said this. The process of finding the derivative of a function is called differentiation. A function is differentiable, so that means you can find the derivative at x if its derivative exists. And it's differentiable on an open interval if it's differentiable at every point in the interval. We'll talk about differentiability in a minute. Differentiability is basically when can you take a derivative and when can you not take a derivative. So what I'm asking you is when can you find a tangent line and when can you not find a tangent line? Okay. So here's our new notation. F prime of x is the most common way that you'll see derivative written. Also dy dx. They're almost equal in terms of how often you'll see one or the other. The reason we have different notations is because two different mathematicians came up with the derivative at two different times. Sir Isaac Newton and Gottfried Leibniz. Isaac Newton was English, British, and Leibniz was German, and they were both working on this derivative problem at the same time. One of them thought of it more as a geometry type problem, so he used the dy over dx. D is difference in y over difference in x, so a real obvious slope implication there, finding the slope. F prime of x was used because this person was thinking of it in terms of a function, not just a slope. So either way, we have to be familiar with both of them because both mathematicians came up with it, and we use both of them. So f prime of x, or we say this is dy dx. It's one thing, it's not dy divided by dx, it's just dy dx. Y prime is another common one. And then d, and then we might put a function in here. So df of x dx is just another way to say the derivative of f of x with respect to x. So what that means is the derivative of some function f with respect to x, meaning it has x in it as its function variable. And this one's very uncommonly used, d with brackets of the function here and then a little x there. We hardly ever use that one, but just be familiar with it. That could be a possibility you might see. So these are the most common ways of writing find the derivative, or the derivative equals this. So that's our new notation. So find the derivative of f of x equals x cubed plus 2x using the limit definition of derivative. Notice they did not give us a point at which we're supposed to find the slope of the tangent line. We're supposed to find an equation that represents the slope of the tangent line that could be used at any x value. So our derivative, which is what we're asked to find, equals, the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So f of x plus delta x. We're going to put x plus delta x in place of each of these things. So I'm going to write that down here. F of x plus delta x equals, instead of x cubed, we're going to have x plus delta x cubed. Instead of adding 2x, we're going to add 2 times x plus delta x. We're putting x plus delta x in place of the letter x. And then f of x is just itself. So let's replace those here. We'll have x plus delta x cubed plus 2x plus delta x minus the original function. Remember to distribute the negative because we're subtracting the whole function all over delta x, and I didn't use an equal sign because I didn't write the word limit again. Now I have to cube that out. I'm going to use Pascal's triangle, the third row, to get my coefficients. So x cubed plus 3x squared delta x plus 3x delta x squared plus 1 delta x cubed. So that is this. And then I'm going to distribute the 2x plus 2 delta x minus x cubed minus 2x. And that's still all over delta x. Simplifying, this x cubed cancels, with this x cubed, and this 2x cancels with this 2x. So now I've got 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x all over delta x. So notice I can factor out a delta x. So I'll have, sorry, don't forget to write the delta x that you're factoring out. 3x squared plus 3x delta x. If I take one of those out, I have 1 left. Take one of those out, I'll have 2 left, so delta x squared. And take that out, I'll have a 2 there. And then delta x. So these delta x's will cancel. And now I'm going to take the limit. So I'm actually going to do direct substitution. Put 0 in for all the delta x's. So I'll have 3x squared. Notice don't put it in for the x, just the delta x. So 3x squared plus 3x times 0 plus 0 squared plus 2. So that simplifies to 3x squared plus 2. So my derivative is 3x squared plus 2. Think about what that means. That is the slope of any tangent line to this graph at any certain point. So if I wanted the slope at the point 1, 3, I would plug a 1 in here, and that would give me a slope of 5. Or if I wanted the slope at 2, I would plug a 2 in here and get the slope. Okay? So we could have done that at the beginning. We could have put a 1 in here and figured it out all the way through like we did the first 2 examples. But this way gives us a general formula for finding the slope of any of the tangent lines that could occur at x to the graph of x cubed plus 2x. And that's called the derivative when you use the x. Find the slopes of the tangent lines at 1, 3, and 2, 12. So we just did that. Let's take this derivative equation, which is 3x squared plus 2. So I want to write that down so I don't forget it. So if I want the slope at 1, the slope of the tangent line at 1, I plug a 1 in there. So that 5 is the slope of the tangent line at the point 1, 3. Or if I want the slope at 2, I would plug a 2 in. 14. So the slope would be 14 at the point 2, 12. Pretty steep there. The alternative form of the derivative is useful for finding the derivative of f at c. You just use the original function minus f of c all over x minus c, and you're finding the limit as x approaches that c. So let's do that example. Looks a little simpler, doesn't it, than without all that delta x stuff in there? It's still the change in y over the change in x. It's still y minus y, y2 minus y1 over x2 minus x1. Okay, so use the alternative form of the derivative to find f prime of x at x equals 2 if f of x equals x squared minus 5. So we're going to do the limit as x approaches 2, this is our c, of f of x minus f of 2 all over x minus 2. So f of x is x squared minus 5. F of 2, plug 2 in here, 2 squared is 4, 4 minus 5 is negative 1, minus negative 1 all over x minus 2. That simplifies to x squared minus 4 over x minus 2. I still can't do direct substitution because I'll get 0 over 0. So I'm going to factor the top, x plus 2, x minus 2, all over x minus 2, cancel them. Now I can do direct substitution, and I get 4. 2 plus 2 is 4. So that's the derivative, or the slope of the tangent line, at x equals 2 of the graph x squared minus 5. If you have an absolute value, we want to find the derivative. First, let's think about how the graph looks. Where will the graph of x minus 2 equal 0? At 2, because x minus 2 equals 0 at x equals 2. And if we're on the positive side of 2, it's just going to be the regular graph of x minus 2. Positive slope, remember absolute value, equals 2 functions really. For x is greater than or equal to 2, it's going to be the function x minus 2. It's going to be the opposite for functions, for the values of x less than 2. So it's going to have if you distribute this in, it's going to have a y-intercept of 2 and a slope of -1. So it's going to be that part of the graph. Okay. We want to find the derivative at 2. Well, check out this graph. It's got this sharp turn right here at 2. Remember, the derivative means the slope of the tangent line. There is no tangent line at a sharp curve. You can't find a tangent line at a sharp curve. Or at a sharp turn, I mean. And the other word for a sharp turn is a cusp. So since there is no tangent line at a cusp, then you can't find the derivative at a cusp. So the derivative does not exist. Here's the first example of where a derivative does not exist at a sharp turn. Graph with a sharp turn is not differentiable. Remember, we talked about that was coming up. So graphs are not differentiable at cusps. So you can never find the derivative at a cusp. Functions are not differentiable at any discontinuity. So think about what we know for our discontinuities. What are the discontinuities? Jumps, holes, oscillations, vertical asymptotes. So functions are not differentiable at any of those places that have a discontinuity. Also, in addition to that, you can also not find the derivative if there's a cusp or there's a vertical tangent line. So remember that graph that had this. This is not differentiable because there is no slope. That slope is undefined. So besides the discontinuities, a graph is also not differentiable at vertical tangents or cusps. If f is differentiable at x equals c, then f is continuous at x equals c. Because, let's think about the continuity, the things that are continuous are included in the things that are differentiable. But there are extra things that make it not differentiable that are continuous. So, the following statements summarize the relationship between continuity and differentiability. If a function is differentiable at c, then we assume it is also continuous. So if something's differentiable, it implies that it's continuous. If you can find the derivative, then you know there's no jumps, gaps, or jumps, asymptotes, holes, or oscillations. It is possible for a function to be continuous and not be differentiable, like at vertical tangents and cusps. At vertical tangents and cusps, the graph is continuous, but it's not differentiable. So if something's continuous, you cannot assume that it's differentiable, because it could be continuous at these things, but it's not differentiable there. Okay? Find an equation of the tangent line to the graph of f at the given point. Graph f in its tangent line and use the derivative feature on your calculator to confirm your results. Yes, your calculator has a derivative feature. Okay? So find an equation of the tangent line to the graph of f. If we want to find an equation of a line, you need two things. You need the slope and you need a point. Going back to Algebra 1, if you want to find the equation of a tangent line, you need slope and point. So we have to find the slope. We're going to take the derivative. That means we're going to use the limit definition. Actually, we can use the shorter form because we know the point at which we want the derivative. So let's do the alternative form. Limit as x approaches 3 of f of x minus, I'm sorry, I want the derivative at 1, not 3. F prime of 1, the limit as x approaches 1 of f of x minus f of 1 all over x minus 1. So f of x is x squared. F of 1, if you plug 1 into x squared, you get 1 squared, which is 1, over x minus 1. That can factor to x plus 1 and x minus 1 all over x minus 1. So you get the limit as x approaches 1 of x plus 1, so we're going to do direct substitution, and you get 2. So now I have my slope, and I have a point, and I can use point-slope form to write the equation of that line. Y minus y1 equals m times x minus x1. So y plus 3 equals 2x minus 2. Continuing to simplify it, 2x minus 5 is the slope of that is the equation of the tangent line to the graph at the point 1, negative 3. Now we can use our graphing calculator to verify the results. On the calculator, you're going to go to Math, push the Math button, and go down to number 8, which says n deriv. It gives you that. So what we're going to do is go to y1, y equals, push your y equals button, and go to y1. Clear out anything you might have in there. And then choose Math. So on your y1, where it says equals, after that you push Math and go down to number 8 and hit enter for n deriv, so it should look like this. And then we want to do the derivative of the function we just had on the previous screen. So x squared. So type in x squared, and then do a comma, and then x. Oops, and then comma x again. This is the variable within the function, and this is which values we want the derivative of, and we want all derivatives of every x. Then in y2, let's put the original function so we can see how it graphs it. Oh, we want the derivative at a certain value, don't we? Yep, we want the derivative at 1. So we're going to put a 1 there. Okay. So x squared in y2, n deriv x squared comma x comma 1. Oh, that's just going to give us the derivative at 1. Sorry. It'll show you a graph like this. It'll give you your x squared, and then it'll give you the line at 2 because that's the slope at 2. That's not what I meant. Your calculator will find the derivative at 1 here for you. So that's your slope, and then we want to multiply it by x, and our y-intercept was 5. So this is basically going to graph the graph of 2x minus 5. This is probably not the best way to do this. What I should have said is that on your home screen, you're going to go to Math, number 8, n deriv, x squared, comma x, comma 1. And hit enter, and that gives you the 2. So that tells you the slope. So you're verifying the slope on your home screen. It's giving you the derivative at any point. And you can use this to verify your answers, but you'll have to show your work for the limit definition. But your calculator can give you the derivative at a certain point. And then in y1, we could just write 2x minus 5. That's what we really wanted to do. Write the equation that we got when we did the derivative and we found the equation. And if you graph it, then it will give you the graph of x squared, and it will give you the tangent line at the point 1, 5. So it'll draw that tangent line on there. Sorry about that. All right, hang on for the homework. All right, there's the homework. You can start working on it if you want to. That won't be due until the next day. So we'll work on this in class tomorrow.